Imagine a delivery robot navigating a campus. A user asks, "Where is the seminar room's printer?" The robot doesn't know the printer is missing. Instead of saying it doesn't know, a modern vision language model confidently outputs a coordinate, and the robot physically rolls to a random spot in the hallway. This isn't just a minor glitch. In embodied AI, overconfidence isn't a bug, it's a deployment hazard. When models hallucinate answers or navigate to arbitrary points, the cost shifts from a simple misunderstanding to physical risk. The core issue is that most embodied pipelines treat refusal as an afterthought. They're optimized to answer, so when faced with unanswerable queries, they double down. Prompting can sometimes coax a model into saying, "I don't know," but it's fragile and highly sensitive to wording. Chain-of-thought reasoning actually makes it worse. By forcing the model to generate intermediate steps, COTI encourages it to rationalize a plausible answer path even when visual evidence is completely missing. Fine-tuning is another route, but it requires curated out-of-distribution data that simply doesn't exist at deployment time. And when models do fine-tune on refusal, they often learn dataset-specific lexical shortcuts instead of understanding what ungrounded actually means. This is exactly where SEMANTICFLIP comes in. It's a lightweight framework that teaches embodied agents when to abstain, without needing any external OOD annotations. The core idea is surprisingly elegant. Instead of hunting for unanswerable examples, you synthesize them by deliberately breaking the cross-modal link between the query and the visual memory. You corrupt one modality while keeping the other intact, creating synthetic pairs that the model should recognize as ungrounded. The framework uses two complementary corruption strategies. First, QFlip. It takes an answerable training pair and rewrites the text query so it can no longer be grounded in the unchanged video. This happens in two flavors. A coarse variant just asks an LLM to generate a question the scene can't answer. A fine variant targets specific abstention categories like referential underspecification, false premises, or subjective judgments. For example, changing "where is the teddy bear" to "where is the stuffed animal" creates ambiguity, or asking "why is the teddy bear on the sofa" introduces a false premise. The video stays exactly the same, but the linguistic grounding is broken. Second, VFlip. This does the opposite. It keeps the original query intact, but corrupts the visual memory so the target object is no longer visible. It runs a strict pipeline. SPACEREJECT extracts the target noun phrase, Grounding-DINO localizes it across the video frames, and then LaMa Inpainting removes those regions. The result is a video where the direct visual evidence required by the query has been erased. When paired with the original question, the model should recognize that the visual grounding is missing and trigger abstention. Here's where the technical efficiency shines. SEMANTICFLIP doesn't touch the underlying vision language model. It uses a frozen encoder, like QN2, 5VL7B, to project both the in-distribution pairs and your synthetic QFlip and VFlip samples into a shared multimodal embedding space. On top of that frozen representation, you train a tiny, 3-layer MLP rejection gate. You only update the weights of this small classifier head using class-weighted binary cross-entropy. Because the encoder stays frozen, the model learns to detect cross-modal inconsistency rather than memorizing superficial text patterns. It's a drop-in module that adds virtually zero inference overhead, and it completely sidesteps the catastrophic forgetting or shortcut learning that often plagues full VLM fine-tuning. To evaluate this, the authors introduced two complementary benchmarks. The first is ABSTAIN, which tests refusal on embodied question answering. The second is SPACEREJECT, a brand new benchmark specifically designed for spatial localization refusal. SPACEREJECT extends existing spatial QA datasets by adding deliberately unanswerable queries over long video sequences. These fall into two practical categories: object-absent queries, where the target never appears in the video, and visually unavailable queries, where RGB sensors physically can't determine the property, like asking for a room's temperature. The results are striking. On ABSTAIN, SEMANTICFLIP with a frozen 7B encoder achieves an F1 score of 0.711. That actually outperforms the strongest prompting baseline using a 32B model, which sits at 0.6746. More importantly, it shows that synthetic OOD supervision makes a practical open-source backbone significantly more reliable than scaling up model size alone. On SPACEREJECT, the framework pushes the F1 score to 0.9559. When you look at the ablations, QFlip provides the heavy lifting for abstention, while VFlip adds a crucial calibration benefit, lifting both recall and balanced accuracy. Let's talk about deployment mechanics. The rejection gate outputs a confidence score, and you trigger abstention when it crosses a threshold, typically around 0.5. The system is remarkably robust to threshold sweeps, maintaining high F1 across a reasonable range. In spatial navigation pipelines, like meta-memory, the gate can be integrated as an in-loop tool. It evaluates the question alongside retrieved memory captions before the agent commits to a coordinate. If the gate scores high, it terminates the loop and abstains. This in-loop configuration consistently outperforms pre-cycle or post-cycle verifiers, because it intercepts ungrounded queries when the agent has enough context to make a reliable veto decision. You might wonder why chain of thought keeps failing here. The data shows that COTI dramatically increases ID specificity, meaning the model becomes very good at answering known questions correctly, but it collapses OOD recall. It essentially trains the model to be overconfident in its reasoning, even when that reasoning is built on sand. SEMANTICFLIP avoids this by learning a structural consistency signal, rather than trying to force reasoning into a refusal task. The approach isn't without trade-offs. Because QFlip and VFlip are fused into a single joint embedding, the gate produces a combined consistency signal. If the model abstains, you can't automatically tell whether it was due to a corrupted query or a missing visual referent. This limits cause-specific feedback for the user. Additionally, VFlip's quality is bounded by the detector and inpainter. While LaMa Inpainting works well, artifacts can slightly weaken the perceptual signal, though experiments show that even cheaper fill operators like mean color replacement remain surprisingly competitive, proving the gate is primarily learning to detect missing evidence rather than discriminating against inpainting artifacts. SEMANTICFLIP represents a pragmatic shift in how we handle uncertainty in embodied AI. By synthesizing out-of-distribution samples through independent modal corruption, it gives vision language models a reliable, computationally cheap way to know when to step back. It doesn't require massive compute, it doesn't break existing pipelines, and it directly addresses the high-stakes failure modes that have held embodied agents back from real-world deployment. The code and datasets are publicly available, making it a highly actionable contribution for anyone building robust, multimodal robotic systems. If you're working on embodied reasoning or safe AI deployment, this framework is definitely worth integrating into your evaluation stack.